If you've never heard of a neural network before, you must have been born yesterday. If that's the case, let's learn the alphabet. Automorphism, space, discrete valuation, vibration, groupoid, homotopy, identity category, J-function, K-theory, elliptic neural network. Neural networks are everywhere nowadays. Image recognition, neural networks. Optimization over a slightly large search space, neural networks. Can't afford US healthcare, neural networks. What's a neural network? Ask a neural network. We've been so preoccupied with computationally modeling the brain that we no longer think to use the genuine article.
Can a robot turn a canvas into a beautiful masterpiece?
Can you?
Neurons network harder than the average linked influencer. If you feel like you can't escape neural networks, you're not alone. Continuous functions know exactly how you feel. So, what's a neural network? Well, you'd never guess, but it's a network of neurons. A neuron takes several input signals and transforms them into output signals. The strength of each signal is scaled by a weight coefficient, and the total signal is shifted by a constant bias. Finally, the sum of the input signals and the bias are fed into an activation function before they are emitted in the output. Like ogres, neural networks have layers. The outputs of the neurons in one layer are propagated to the inputs of the neurons of the next layer. These intermediate layers are called hidden layers because we can't see them. In some sense, the input and output layers of a neural network are like the driver's wheel and the tires of a car, and the hidden layers make up the car engine. While the driver's wheel and the tires have defined roles, the engine is something that most people don't understand, but they trust that it works. By passing the inputs through layers and layers of weights, biases, and activation functions, a neural network computes a function from Rn to Rm. As far as applied mathematicians are concerned, reality is just a bunch of probably continuous functions from Rn to Rm. Of course, the real world is a nasty place, and most continuous functions are quite ugly. So one would hope that we can approximate general continuous functions with nicer ones. If you're the kind of person who thinks neural networks are nice, don't worry, this is a safe place, and we're not here to judge you. You'll be pleased to know, if you don't already, that neural networks can approximate arbitrary continuous functions. This is the meat of the universal approximation theorem. Before you get too excited, please be aware that neural networks are by no means the only, nor necessarily the best, approximations to arbitrary continuous functions. I personally really hate the name of the theorem. It gives so many wrong impressions. The universal is not even in the sense of a universal property of neural networks, disappointingly. Calling it the universal approximation theorem makes it seem like neural networks are somehow a really special or inevitable subclass of continuous functions for approximation, especially since neural networks are not mentioned anywhere in the theorem name. Why not call it the neural network density theorem, or the fundamental theorem of neural networks if you love it so much? Do you know what else approximates continuous functions on a compact set really well? Lines. That's even how most graphing software works. Could you imagine if they used neural networks? A much nicer class of continuous functions, in fact about as nice as it gets, is the class of polynomials. Polynomials too can approximate continuous functions to arbitrary precision. No, I'm not talking about Taylor polynomials. Even the spikiest continuous functions can be accurately approximated by polynomials. This is a consequence of the Stone-Weierstrass theorem, but we can also construct polynomial approximations quite easily. In one dimension, after squishing and translating, we can focus on the interval 0, 1. Now we can approximate the function to arbitrary precision using Bernstein polynomials. That being said, it might take a large degree to approximate the function well. In fact, if the continuous function is differentiable, then the Bernstein polynomials will also approximate the derivative. So take that, Taylor. For higher dimensions, the situation is pretty much the same. So if we have lines and polynomials for approximating functions, then why even bother with neural networks? Well, I don't know, man. I just work here. The reason lies not in approximating continuous functions that we already know, but rather in approximating continuous functions that we're trying to learn. The problem with polynomial approximation and linear interpolation is that they tend to overfit the data, whereas neural networks are known to generalize relatively well. We're more interested in approximating known continuous functions, so we won't be seeing this side of neural networks. In fact, the real heroes in this video are the polynomials. If you're not in the neural network business, you might be surprised to find out that it doesn't take a lot of depth to understand continuity. If we want to approximate a continuous function from Rn to Rm, we only need a neural network with one hidden layer to do so. Well, this is not always true. If the activation function is a polynomial of degree d, then any neural network with one hidden layer is going to be a polynomial of degree at most d as well. However, if the activation function is pretty much anything else, then one layer is enough. Usually, mathematicians go about proving things backwards, by simplifying a problem in stages until you get to the meat of the problem. This is especially useful for organizing thoughts and makes a proof much easier to read. This is not what I'll do. We're going to go in order, starting from humble beginnings until we get all the way to fully general continuous functions. For simplicity, we will assume that our activation function ρ is infinitely differentiable, but still not a polynomial. Now that we have rejected polynomial activation functions, the first thing we're going to do is recover polynomials. Since our activation function ρ is differentiable, we can approximate the derivative of ρ of wx plus b with respect to w, where x is the input and b is a secret tool that will help us later. Recalling from first year calculus, we can have the neural network approximate the derivative using a secant line calculation. A small enough choice of h will give us as good of an approximation of this derivative as we'll need. Once we have an approximation of the first derivative that's up to par, we can use it to get a decent approximation of the second derivative. The secret? Taylor. We can then repeat this process to get arbitrary derivatives to whatever precision we need. From the chain rule, we can approximate the monomial x to the k using a kth order derivative. The only catch is that we have to make sure that the kth derivative of ρ at b is non-zero. This is where we use that ρ is not polynomial. Any non-polynomial smooth function can be hit endlessly with derivatives and never go to zero. Therefore, we can always find an appropriate bias b so that the kth derivative of ρ at b is not zero. In fact, a random choice of b will almost surely work. Now that we have monomials, getting to polynomials is very straightforward. If I have a neural network that can approximate g1 of x, and I have another neural network that can approximate g2 of x, then I can construct a neural network that can approximate any linear combination alpha times g1 plus beta times g2. In particular, I can approximate any polynomial by taking a linear combination of approximations of monomials. To pump up the input dimension, we stretch and try spinning. This is where the fun begins. To point a single variable function g of x in the direction of a vector a, we use a ridge function g of a dot x. If I have a neural network that can approximate a function g of x, then I can modify it into a multivariable neural network that can approximate the ridge function g of a dot x. In particular, from step 1, we can use neural networks to approximate a dot x to the power of any k. Using the tools from step 2, we just need to show that any polynomial in multiple variables can be written as a linear combination of these a dot x to the k. Let's first show this is true for homogeneous polynomials in multiple variables. These are the polynomials where each term has the same total degree. Note that the ridge function a dot x to the k is actually a homogeneous polynomial of degree k. The name of the game is to show that these ridge functions span the space of all homogeneous polynomials of degree k. We do so by studying the linear functionals on this space. We will show that the only linear functional that kills all ridge functions is the zero functional, and this implies that the ridge functions generate the entire space. Since the monomials of degree k form an obvious basis of hkn, the corresponding differentials of degree k form a basis for the dual space of linear functionals. In particular, we can view any linear functional L as a homogeneous polynomial in differential operators. Through the power rule, we find that applying our linear functional onto a ridge function a dot x to the k is the same as evaluating the corresponding polynomial at the direction vector a. In particular, if the linear functional annihilates all ridge functions, then the corresponding polynomial must be zero, and therefore the original functional must also be zero. This is exactly what we wanted to show. Now, since a general polynomial can be written as a sum of homogeneous polynomials of different degrees, it follows that arbitrary ridge functions can span the entire vector space of polynomials.
Another happy landing.
Now that we have access to polynomials, we can use them to approximate arbitrary continuous functions. We can do so using the Bernstein polynomials mentioned earlier. The last thing we need to do is pump up the output dimension. Luckily for us, this is not nearly as difficult as step 3. A single continuous function from Rn to Rm is just a vector of m continuous functions from Rn to R. All we need to do is approximate each of the coordinates separately and then stack all of the neural networks together. And there you have it, a complete algorithm for approximating an arbitrary continuous function using a neural network with a smooth but non-polynomial activation function. If you're still here, thank you for watching, and please make sure that you drink plenty of water after this. If you're wondering what happens if the activation function is not smooth, then go read the original manga. The argument is not too complicated, but you could say that it's a bit convoluted. If you liked the video, color me surprised, but I'm told there's a way you can express that somehow. If you didn't like what you watched, that's cool. I'll still have that one fan to back me up.